In the last lecture, we talked about the Gauss lemma. Today, we will further the discussion and the below topics will be concerned. First, the second Gauss lemma. Second, Newton's theorem. Third, Sophie-Germain identity. Polynomial factorization is a very important method. It is widely used in many math contexts. It appears simple, but there is something difficult inside. In the last lecture, we solved some of these problems. Today, we will use some of the three new methods and solve some other problems. Most of them are IMO problems. Before we go to introduce the second Gauss lemma, let us review the first Gauss lemma in factorization we talked last time. Say fx is a polynomial with integer coefficients, and if fx equal to 0 has a rational root. Here pq are co-prime integers, and then we must have p divided a0 and q divided an. Say, suppose exists root x equal to p divided by q, and p not equal to 0, pq integer. Then we have fx equal to x minus p divided by q and multiplied by qx. Here, qx is also a polynomial with integer coefficients. Then we have q fx equal to qx minus p qx. If we can let x equal to 1, then we have q f1 equal to q minus p q1. Because pq are co-prime integers, and q1 is also an integer, then we get the conclusion q minus p can divide f1. Same way, if we let x equal to minus 1, then from here q f minus 1 equal to 1 minus q plus p q minus 1. We notice q minus 1 must be an integer, and pq are corporate, so we get the conclusion p plus q divide f minus 1. These two conclusions are called Gauss lemma 2 or Gauss lemma extension. In the last lecture, we introduced Gauss lemma 1. So in real polynomial factorization, we can use all of them together to narrow down the result. See this example. 6x3 minus 5x squared plus 5x minus 2. Obviously, if x less than 0, fx will be less than 0, because this is become negative, and this is negative, this is negative. All of them are negative. That means x must greater or equal to 0. Simply x greater than 0. Now we know a0 is minus 2, an is 6, because p divide a0 is p divide minus 2. So p can only be 1 or 2. We don't need to think about the negative values, so p can only be 1 or 2. For the q divide an, which is minus 6. So q is 1, 2, 3, 6. Same thing. We don't need to think about the negative. So Q is 1, 2, 3, 6. So the possible x value is 1 divided by 6, 1 divided by 3, 1 divided by 2, 2 divided by 3, 1 or 2. Sure, the x values can only be one of the 6 numbers. So we can put 1 by 1 to try if it is 0, and we can find the correct answer. But here, we want to show how to use the Gauss-Lemma tool, so we still go with the Gauss-Lemma tool's way. And we notice F1. F1 is 6 minus 5 plus 5 minus 2. It is 4. Sure, it is not 0. So 1 is not a root. So we can omit this one immediately. F minus 1 is 16, 5, 5, 2. It is minus 18. If we omit the negative, so we can think it is 18. Now we calculate Q minus P and Q plus P for each of the values. So for 1, 6, Q minus P is 5. And for 1/3, Q minus P is 2. For 1, 2, it is 1. For 2, 3, it is 3 minus 2, it is 1. For P plus Q, it is 7. Plus, it is 4. Plus, it is 3. Plus, it is 5. Okay, we calculate the Q minus P and Q plus P. For example, for the first one, Q minus P is equal to 5. And Q minus P is 5. 5. Can it divided by F1? F1 is 4. 5 cannot divide 4. So 1 divided by 6 is not an answer. Let me see this one. So for this one, let me see Q plus P. Q plus P is equal to 5. And Q plus P, we see if it can divide F minus 1. F minus 1 is 18. Obviously, 5 cannot divide 18. So 2 divided 3 is not a root. So for now, only 2 options left. One is 1 divided 3. One is 1 divided by 2. We can test. Suppose we test this one first. 6, 3 square plus 5 minus 2. This is 3 minus 5 is 2 plus, and this is equal to 0 because this is 1 divided by 2, so it becomes 4 divided by 2, so it is 0. So this one is a root. If this one is a root, this one may be not a root. Anyway, we can still try this one, and we find this one is not a root. 1 divided 3 is not a 0 for the fx, so x equal to 1 divided by 3 is not a root. Next, we use a long division method to get the rest factors. We write the function together right here. The left side is x minus 1 divided by 2. The right side is the existing equation. And here we use 6x squared, and it multiplied by x, it becomes 6x3 minus and 3x2. It becomes 0, and this becomes minus 2x squared, and this can come down plus 5x. And here we use minus 2x, and it becomes 2x squared, and this one becomes plus x. And it minus, so that becomes 4x. It comes down, it becomes minus 2. And then we use 4. So it becomes 4x and minus 2. And we get 0. So we can use this way. It is equal to x minus and 6x squared minus 2x plus 4. We put the 2 over here. It becomes 2x minus 1. 3x squared minus x plus 2. Please note, the Gauss-Lehmann method is also named as the Newton theorem by someone. Here is the tips. We can think about the possible values range first, and limit the root number in a short period, and then we can use the Gauss-Lehmann method to focus on the correct result. Below is an example to show how to quickly get the result. You use Gauss-Lehmann method together with the range valuation method. Example 2. Fx equal to 2x to fourth power plus 5x to third power minus x squared plus 5x minus 3. We want a polynomial factorization. The first step is about the value range. Then with f0 is equal to minus 3. F minus 1 is 2 minus 5 minus 1 minus 5 minus 3, and it is minus 12. And F1 is 2 plus 5 minus 1 plus 5 minus 3. It is equal to 8. Obviously, f minus 1 and f0 less than 0, but f1 greater than 0. So must have a root at below 1 but greater than 0. And this one we can say it is p divided by q. So you can think pq both greater than 0. Next step, we use Gauss-Lehmann method. So an is 2, a0 is minus 3, and p divide a0, and so p divide 3, and p greater than 0, so p can only be 1 or 3. Same thing, q divide an, q divide an, and an is minus is 2, and q greater than 0, so q is 1 or 2. That means p divided by q can only be 1, 1 divided by 2, 3 divided by 2. But we know x less than 1 greater than 0. So the only possible value would be 1 divided by 2. So we can only check if 1 divided by 2 is okay. So we just check fy divided by 2. It is 2 fourth power plus 5 2 3 power 2 square 2 minus 3. And this is the first and this is 1 divided by 8. So plus this one is 8, 6 divided by and this is 3 divided by 4. So it is minus this one, 2 divided by 4. So this is really 0. That is 0. This is 1 divided by 2. So 3 divided by 2. So it is 0. So f is 0. That means x minus 1 divided by 2 is a factor. The third step, we use the long division method to get the other factors. We write the polynomial over here and x minus 1 divided by 2 over here, and then we have 2x3, and this is 2x4, and minus x3, and this is 6x3 minus x squared, and then we can use plus 6x squared, and this becomes 6x3 and minus 3x squared, and this is 2x squared, 5x, and here plus 2x, and this is 2x squared minus x, and this is 6x minus 3, and then plus 6, so 6x minus 3, so it is 0. Therefore, we get the factorization result. We can put the 2 over here, and then we have it is equal to fx 2x minus 1 and x3 plus 3x2 plus x plus 3. And for this one, we can still use the Gauss-Lemma method, but because it is simple, we can write down the result immediately, because it both has x plus 3, x plus 3, x squared, plus x plus 3. And then we have x plus 3 and x squared plus 1. And this is the final result. In a word, if we can use multiple methods together and combine them efficiently, we can quickly get the result. Today, we will introduce Sophie Germain identity. This is the Sophie Germain identity. Sophie Germain is a scientist a few hundred years ago. Sophie Germain identity looks simple, but it is widely used on a lot of math contests. So today, we will use her method to solve at least 7 problems. All of these problems are math contest problems. Some of them are IMO problems. Let's review the method first. So x to fourth power plus 4, y to fourth power, and it can be, and then we get this conclusion. Okay, we use this method as a theory to solve the first problem first. What is the remainder? 1 2 to 202 power plus 202 is divided by 2 to the 101 power plus 2 to 51 power plus 1. Let's set y is equal to 250. Therefore, 202 plus 202 become 4 y to fourth power plus 202. Because 2 to 202 power is equal to 2 plus 200 and equal to 200. And then this is 4. This is y to fourth power. So the first one is 4. And for 101 plus 51 plus 1, it is 2 multiplied by 2, 100 plus 2, 250 plus 1. And this is 2y squared plus 2y plus 1. Let us look at this identity. So we have 4y to fourth power, and x we don't have x. We let x equal to 1, and then this become x to fourth power plus 4y fourth power plus 201. And the first section we can use this equation. And the x is equal to 1, so we have compare this to this, so this part can be cut off. So the remainder is 201. Okay, let us look at the second problem. This is the next example problem. Prove that if n greater than 1, then n to fourth power plus 4 to nth power is a composite. Let's compare n to fourth power plus 4 to nth power with x to fourth power plus 4y to fourth power. Obviously, n is the same as x, and we hope 4 to nth power is same as 4y to fourth power. Luckily, 4 is 2 to 2 square, so 4 to nth power we can change it 4 n minus 1, and 4 2 n minus 1. So here we hope 2 n minus 1 can be same as y to fourth power. And if we divide it by 2's power, and means 2 to n minus 1's power should be the same as y squared. Means n minus 1 must have a factor of 2. Means 2 can divide n minus 1. So that means we should think about n with even or odd in two cases. Odd number or even number. And we think about if both of cases, this number is a composite. Now we go with the solution. If n is even, then we have n to fourth power. So this number can be divided by 2 if n is even. In that case, it is a composite. So we can suppose n is odd. And then we let n is equal to 2k plus 1. Here k is an integer. And then we can change it to this way. So n to fourth power plus 4 to nth power is equal to n to fourth power plus 4. 2k plus 1. 2k plus 1, the 1 is over here. And 4 to 2k's power become 2 to 4k's power. So we have 4 over here. So we can think x equal to n, y is equal to 2 to k's power. and we can apply this identity, self-German identity, and we immediately get this factorization result. That means this must be a composite. Let's go to the next problem. This is a problem in 1987 AIME, question 14. Compute this big number. Let's watch it closely. We see everywhere there's an item 3 to 4, and 3 to 4 can be rewritten as 4 multiplied by 81. It is 4 multiplied by 3 to 4th power. So looks like it is close to 4y to 4th power. And look at the upper side and the downside. The upper side is 10, 22, 34, 46, 58. And the downside we have 4, 16, 28, 40, 52. What we can find? Everyone in the above one. This one minus this one is 6. This one minus this one is 6. 6, 6, 6. So the upper one minus the below one always 6. So must have some one. If we can polynomial factorization the upper side, possibly we can immediately cut off something. So the question becomes how to factorization the upper side and the lower side. For all of these 10 items, we apply this equation. Then we have, after we simplify, and we can see the upper side and the lower side, it can be cut off like this, like this, like this. Always cut off, same thing. And the last one, 52, 58, 52, 58, cut off. So only the last item in the upper side and the first item in the downside, in the lower side, are left. So the last result is 373. Okay, let me go to the next problem. The fourth problem, find the largest prime divisor of 5 to 4th power plus 4 multiplied by 6 to 4th power. AIME, question 5. Obviously, we can use it immediately, and we have x equal to 5, y equal to 6. Then we have 5, 4 plus 4, 6, 4 equal to 2, 6 square, 2, 5, 6, and 5, 2 plus 2, 6 square plus 2, 5, 6. See the largest prime divisor. So we think about if this one is a prime, and 5, 2 plus 2, 6, 2 plus 2, 5, 6, 25 plus 72 plus 60. It is 25, 72, 60, 6, 1, 5, 7. 1, 5, 7 less than 225. So we're going to check the number below 15. If anyone can divide 157, so 3, 7, 11, 13. And we know each of them cannot divide 157. So it is a prime. Look, the next problem. Prove that there exist infinite natural numbers n fulfilling the following property. For all natural numbers n to fourth power plus n is not a prime number. This is IMO problem in 1969. It looks very simple because we can set m equal to 4 t to fourth power, and t is an integer. And from a Sophia-German identity, we can have n4 plus m equal to n4 plus 4t4, and it is n squared plus 2t2 minus 2nt, n2 plus 2t2 plus 2nt. Obviously, it is two-factor numbers, so it is a composite number. So this problem is immediately solved if we use the Sophia-German identity method.